In this video, we're going to take a look at how we can implement printf inside of our current operating system code. Printf is going to let us get a lot of functionality for printing out like integers and these types of values, which is going to be helpful for us generally to be able to work with our operating system for things like debugging and seeing information pass between assembly and C. Now, the implementation of printf is a little bit complex. There's a lot of moving parts to it, so we'll see a lot of different details associated with this. And generally, I'll also say that the printf that I'm going to be implementing is going to be a bit of a simplified version of it. So starting off, we'll just make sure that we have a good understanding of printf. So printf has a bunch of different formats that are associated with it. And when you call printf, you give it a string with some formats or some text or some combination of those two things, something like this, for instance. And then you give it some values to place into those formats. And what it will do is it will move each of these arguments into the respective format that matches it in this kind of format where the first thing in the arguments list goes to the first format and so on and so forth like this. Now, there's a lot of different formats that exist, and some of them are just single letter ones like %c, which is character, or %s, which is string. But then there are some that are multiple characters like LD, which is a long integer, or LLD, which is a long integer, and so on like this. So we need to be able to parse all of these different strings. And one of the easiest ways for us to parse strings is actually using this idea of a state machine. If you don't know what a state machine is, generally it's basically a way of moving between different states and taking different actions based on what state we are currently in. And that's the approach that we're going to take for implementing our printf function. So to start off, I'm going to define out all the different states that I want to use inside of my stdio.h file. Now, the definitions of these, the naming of them isn't necessarily important. We just need to understand what they represent. So when we start printf, it's going to start off inside of this initial state, which we're going to call printf state start. As we're going through, there's a few different things that could happen. The first thing is that we encounter one of our format strings, in which case we want to determine the length associated with that format. So assume that you encounter a percentage sign, which is the indicator that a format is going to follow. If we see like %sign, then we know that we're looking to see what the length of that is going to be. So for instance, %d would be of integer length is the idea. Now, some of these, like I said before, have special cases where there are more than one character. So if we see a character where another one might follow, we're going to go into a specific state associated with that. So we'll have one called short, and we'll have one called long. And what these are going to be associated with is they'll be associated with cases where we have, so we could have %hd or h something like this. So the h indicates the short version of what follows. So if we see an h, what we're going to do is we're going to move into this state here, and we're going to search for the next value to get like the full length string. And similarly, if we see an L at the start, then we know that something else must follow it. So what we're going to do is we're going to look for that next character, and then we're going to parse it off. Now, there's also going to be a few different constants or states that we're going to use to define the actual length of the thing that we're parsing. So the start of that is going to be 0. And then we're going to have a few different states that could come up that are important to note about. So we have printf length short. This is representing the case where we have two short characters, so like HH and then something like HHD would be like a short integer, for instance. So that would be an example of a short. And then we have just like an individual single short. So that would be just this value here. And we'll make that 2. And then similarly, we do the same thing for long. So we'll have long, which I'll give a value of 3. And then I have long, which I'll give a value of 4. So those are all the different states that we're going to work with. And don't worry, these states will become a bit more clear as we actually implement printf, how these are actually working. So the final thing that I need to do here is I just need to add in my function stub, right? So generally, the function for printf is going to look like this. It's going to be c decal printf const char star format. So it takes in a format string, and then it takes in some number of arguments that follow this. So it's going to take in that format string, some number of arguments that follow it, and it's going to use that to actually parse the string that we're looking to parse. So that's the general setup inside of the header file. Now let's go over to the C file and take a look at what that setup looks like. In the C file, what we're going to do is we're going to start by declaring out our function for printf. So we'll do a cdecl printf. It's going to match the exact same declaration as the header file, of course. And we take in a format string and, again, some number of arguments. And what we start by doing is we start by setting up a pointer, which I'm going to call argp, which is going to be equal to an int pointer to format. We're going to use this throughout our parsing just to keep our track inside of that format string. We're going to initialize our state to be equal to printf state start. So we'll set it up for the start state, and we'll set up our length to be equal to printf underscore length default. So those are, length start was what I called it. Yeah, length start like this. So those are the two things that we need to set up for our state. And then there's a few other variables that we're going to need throughout this. There's one that I'm going to call radix, which will set equal to 10. And there's one which I'm going to call sign, which I'm going to set equal to false. Now, radix is being used to parse out numbers. If you think about a number that we would need to print, something like, I don't know, 453. What I need to be able to do is I need to be able to extract each individual character from this in order to print it. The easiest way to do that for a number like 453 would be to divide by 10 consistently, getting each of these different digits. You'll see how that process is generally done, but that's what the radix is generally doing. And the reason why we declare this, it's not always going to be 10, right? If we have hexadecimal values, like 1A, for instance, this is actually a base 16 number. So to get each individual digit, we divide by 16, right? So that's why we're defining this as a variable, since it might change over time. Now, the sign is indicating if the number is positive or negative, or if it could potentially have a sign, really. So, like we could have a number like -10, for instance, so we want to accommodate that negative sign. So that's what the Boolean sign is doing. Now, if you've sort of noticed, C doesn't have Boolean types, right? So we actually need to implement a Boolean type, which we'll do inside of stdint.h. So the way that I'm going to do that is I'm just going to do a type def for uint8 underscore t bool. And I'm also just going to define a value true to be 1, and I'm going to define a value false to be 0. This is going to get us set up with the true and false types, as well as our Boolean. So now turning our attention back into our main code here, what we're going to do is we're going to be working with argp, which will increment at the start. And then I'm going to loop through this while there's still things left on the format string to parse. And we're going to parse these things through with case statements. So there's a few different cases that we're generally going to have. So we're going to have the state start, right? I'm just going to write out each of these because it'll be a bit easier to do once we have them all written out, just to keep track of everything. So we'll have the state for length. We have a state for what we call state length short, or state short rather. And then we have a case for state long like this. So these are just the states that we have. I'll just put in my breaks. That way I don't forget them. Always when I'm working with case statements, I like to write out my cases and then my breaks, because otherwise I'll forget my breaks and then we'll get errors, and we want to try to avoid that. So at the start, what we're looking for is we're looking for a % sign. So generally what I could do is I could say if, star fmt is equal to the % sign. And what I could do is I could set the state equal to printf underscore state length, because now we're checking to see what the actual length of that format is going to be. If we don't get that % sign, well, what I'm going to do is I'm just going to put C with that format variable. So I'm just going to simply print it out. Now, I just want to note that, in some cases, you might see this part written out as a case statement. I think because we just have two conditions, it's fine to just use an if statement, right? But you could use a case statement here too if you prefer to do so. But that's just up to you, really, the options there. Now, similarly, we want to take a look at our states for the length. Now, with the length, we really have two main things that could happen. We could see an L, we could see an H, or we could see nothing associated with either of those two. If we see an L, it tells us that something that follows could be, like a D or something like that. So we know that the L is really just indicating the length. Whereas if we don't see that, if we just see like D, for instance, we know that it's just a type and we can move on from there. So that's the general idea of this portion. So again, I'm going to do this as an if statement. You could do it as a case statement. It's really up to you which way you want to go about it. Since there's just three conditions to check, an if statement is probably fine for this. So if we get the value h, what I'm going to do is I'm going to set my length equal to printf length short to specify that this is a short length, since that's what h is associated with. So it's just, letting us know that this value is going to be potentially short in value, right? For the state, I'm going to set it to printf state short, like this. So that's going to take us into this state right here. What this state is going to do is it's going to check for further values associated with this h. So that's what you'll see happening in there. Now, in the else if, we're going to check if the format is equal to L, right? If it's equal to L, that tells us that we're actually in printf length long. And we would set the state equal to printf state long. So that's going to be associated with this case right here. So in the general case where we don't have any of these values, it's not an H or an L, then we're actually going to do a goto. And that goto is going to be to printf state spec, which is just like a special area where we can actually, parse through and, work through the actual format string itself. So this basically says we're at the end of parsing the format. Now we can move on from that portion. Now, if we did have a case where we were in short, which means that we saw an H as our first character, we are then going to check to see if there is another H. So if the format is equal to H, once again, then the length is going to be equal to printf length short, right? So it's going to be short like this. What this is really capturing is it's capturing the case where we have something like HHD, right? So we saw the first H up here, and then we come down here, and what we're looking for is that second H. If we see that, it tells us that the length is a short, so it's smaller than a short, right? Whereas if we see just a single H, it would tell us that we're actually just a short, and we can move on, right? At this point, the state is going to be equal to printf state spec, which I actually don't think I defined inside of the header. Yeah, I didn't. So I need to define that as well. Basically, the printf state spec is just going to be saying, okay, we're done looking at the format. We can move on to the rest of the parsing. So that's generally what this state is representing. So if we see the H, then we set the length to short. Otherwise, well, this length can remain the same since it's already set to short. All we really have to do is we have to go to that printf state spec like this. So that's going to take us to the end. Now, similar type of process inside of our state long. Again, what we can do is we can say, okay, rather than looking at H, we're looking for an L now. This is covering cases where we have things like LLD, for instance. We saw the first L up here. We're looking for the second L to see if it's a long, or to see if it's just a long. That's what we're really doing here. So we could do printf length long, since that's the length that we now have. And then this state remains the same since we're done parsing the format. And then this stays the same as well, since we could jump to this generally if we don't see this second L. And that gives us all of our cases here. Now there is one other case that we want to cover, which you've seen here. It's the state spec case. And inside of this is where we're going to put that spec label. So it's the state spec label. So basically when all these go-tos happen, they jump us right over here. So they just take us straight into this code. And what this code is going to be looking for is it's going to be looking for the remaining formats. And in this case, I think a switch statement makes a lot of sense because there's a lot of different cases that could exist. I'm going to lay these out for you. We have a case for C, a case for S. C would be character, S would be string. And then we're going to have a case for a % sign. You could have 2 % signs, and in that case, we just print out the % sign. It's basically going to escape character for the %. We could have a case for integer values that are signed, which there's actually 2 possible values for. There's D and there's I. Both of these are unsigned or are signed integers. And then U would be our unsigned integer. We have cases for hexadecimal values. There's a few different cases for these. There's an uppercase X, there is a lowercase x, and there's a p value like this. So those 3 are all the same case. There's a case for O, which is octal, and then there is just a default case, which will be just to break. So these are all the different cases that we have. So a lot of these are pretty easy, right? Like character generally is going to be a pretty easy one. All we're going to do for this is we're just going to do a put C for the character of argp. So we're just going to print that character, and then we're going to increment argp, and we're done. String is similarly relatively easy, but there's some interesting things that we need to consider for string actually. So the thing that we actually need to consider is the length of the string. If the string is length long, or if the length of the string is long, like this, there's actually something that we really need to consider with this, which you may or may not be familiar with, depending on how much low-level programming you've done. But there's this idea of a far pointer, and a far pointer basically points to something that is generally outside of, I believe it's like the main memory structure that we have. So it points to something that's larger than the general memory size that we have. So in this case, long and long would fit into those categories. They actually use a far pointer. So to print these, we have to do something slightly different. We're actually going to use a different puts function, which we'll actually have to declare here as well. So we'll have to do that here. We'll do that in just a moment. But generally what it's going to do is it's going to format the thing as a far double pointer like this of argp. So that's the way that we need to print those values. And then as well, argp doesn't just increment by 1. It increments by 2. That's just based on how much space these arguments actually take up. They take up the 2 spaces rather than the typical 1 space here. So that's why we increment this by 2. Now the second case for this, which is, it's not a long or a long, we can use our normal puts function, and we can use a normal char pointer like this for argp. So that case is pretty easy. And we increment by 1 only since it's a smaller size compared to this. Now this printf function is actually a very easy function. It's the exact same as our normal puts function, just that the pointer changes, like the way that it actually works. So rather than doing a const char star, we do a const char far star like this. Next to that, everything else stays the same. So it's not too complicated. It's very similar, right? Now I'm going to move this so that I can get the stub inside of my header as well. So to make sure to put that inside of here. Code will still work without it, but it's good practice to have it in there, just to have it defined. Now, what about the other cases that we have? So that takes care of our string and our character. For this %sign, we have a very easy case. All we have to do is put C the %sign. So we just put that character onto the screen and we're done. For integer values, we need to provide a radix and sign. So the radix would be equal to 10 for decimal values. The sign would be equal to true because D and I can both be signed. So they could have a sign, so we set that equal to true. And then what we're going to do is we're going to call another function. And it's going to be called printf underscore number. It's going to take an argp, the length, the sign, and the radix. And it's going to use those to print the number. And we'll implement that a bit later on here. We'll just finish up these cases. So unsigned is the same sort of deal. It's a decimal value, so radix can be 10. And sign would be equal to false for this, since this is an unsigned value. We'll use the same function to print it, so nothing else has to happen there. Now for these ones, x, and p, these are hexadecimal values, which means that they are base 16. So they're base 16, they can't be signed, so sign would be equal to false, and everything else remains the same. Finally, octal. Octal has a base of 8. It doesn't have a sign, and we can use the same print function for it. With that, we have our sign and radix all set up, so those are all the cases we need to handle. From here, what I'm going to do is I'm just going to set the state back equal to the initial state, so I'll call it state start. I'm going to set the length back equal to the starting length. And then I'm going to reset the radix to 10 and the sign to be equal to false. And that's about it. And then we have a break here since this is the end of our switch statement. And there we go. So that's everything that we needed for this general section of the implementation. The next thing that we're going to implement is print number, which I'm going to place directly below the standard io.h. So what I'm going to do is I'm just going to copy this here so that I can grab that definition. And what we need to do is we need to create a an array of all of the possible characters that we could have. So all the possible characters would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the hexadecimal values, A, B, C, D, E, F, like this. The definition is going to be, we're going to return an int star. The function is called printf number. We take in an int star argp. We take in an int length. We take in a Boolean sign, and we take in an int radix. And just before we implement this, I'm just going to move it over to my header as well so that I have that inside of here. So in the stdio.h header, we're going to place this in here. So this is an int, this is a bool, this is an int, and this is an int star. So there we've got our header set up there. Now the way that this code is generally going to work is it's going to store everything inside of a buffer, and that buffer is going to be 32 in size. That's generally going to be the main size that we're going to be working with these numbers, so we're going to use 32 for this. We're going to have an unsigned long named number, which we'll use for parsing our numeric data. We're going to keep track of the sign, which I'll initialize to 1. I'm going to keep track of the position in the string, which I'll initialize to 0. I'm going to do a switch based on the length, since each different length will be parsed slightly differently. We have a few different cases. So we have the printf length short. That goes into the same sort of case as the printf length short. So these two are the same, as is the length start, so the default length that we have. So all of these really work the exact same way as each other. So they all go into one case, and I'll place my break here so that I don't forget. I want to have a case for the length being long. And then I'm also going to need a case for long. Okay, so I have a case for printf long. So that should be all the cases that I need. Now it seems like I might have mistyped this. Let me just make sure. So printf length underscore start. There we go. Just make sure that that is okay. Okay, cool. So that's looking good now. So this one should be printf length long as well. So just make sure that we got all those correct. Should see syntax highlighting. There we go. So this case here, what we do is we start by checking if there is a possible sign for this value. If there is a sign, then we're going to set n equal to argp. And if that value is less than 0, then n will be equal to negative n. So we're just going to flip it so that it's the positive value. That way we can get the magnitude of the number. And we'll store the sign inside of number sign, which I'll set equal to negative 1. From here, we'll parse out the number. We'll set it equal to an unsigned long of n. So that's how we'll parse out that number. Now the else statement here is generally going to be if it's not a signed value. If it's not a signed value, it's just going to be a little bit smaller. So it's going to be an unsigned int of argp. So you see that basically the main thing that changes was the typing between these and us using pointers here. That's really the main things that are changing between those two cases. Now the next case that we have is printf length long, and it actually looks very similar to this. So I can just kind of copy this over. And generally what we're saying is if there is a sign, we once again are going to take this value, but we need to use a different type. We need to use a long int in this case. And this here needs to be parsed as a long int star of argp. If n is less than 0, we once again flip it and change the sign. This here would be an unsigned long, so that all looks good. This would be an unsigned long int in this case. So that's what's going to adapt here. Now, there's one other thing that I realized I forgot here. I need to increment argp as I'm going through this, right? So here argp increments by 1. Here argp is going to increment by 2 because the long is larger. So it needs to increment by 2 rather than 1. Now printf long, again, is going to follow a very similar pattern. Main differences here is that rather than this being a long int, it's a long int. Once again, this right here is going to change a little bit. It's going to become a long int like this. If n is less than 0, n becomes negative n. This becomes negative 1. This number becomes an unsigned long of n. That all looks good. Otherwise, this becomes an unsigned long int of argp. So that's what's going to adapt here. Finally, to increment argp, we increment argp by 4. Again, because this is generally twice as big as a long, so it's going to be twice as much of an increment. Now that we have all of that set up, all we need to do is parse out the number and print it. So what we're going to do is we're going to set up a do while loop. What that loop is going to do is it's going to set up this variable called remainder. And we're going to call a function called x86 div 64 32. It's going to take it a few arguments, a number, a radix, a pointer to a number, and a pointer to a remainder. Now, the reason why we're calling this function, which we'll implement actually in assembly, is because the division operation that we use in C makes some assumptions about the sizes of the data and the sizes of the registers that can be used. We actually need to force it to use the proper sizes, which is why we're going to implement this ourselves. So we have to do a bit of long division algorithm on our own. It's not too bad to implement, you'll see once we start to work on it. But generally, once we get a result from this, I'm going to place that result into the buffer, and that buffer will be equal to the possible values. What did I name that array? I named it possible chars at the remainder. So generally, the remainder is going to serve to index inside of our possible characters array. So it's going to give us one of these characters back as a result. And we're placing these inside of this buffer, and it's going to end up placing it in reverse order just because of the way that it parses off the digits. It parses from right to left as we divide, which generally is going to mean that it's going to, give us the numbers in reverse order. So when we actually go through and try to print these values, so we repeat this while number is greater than 0. And when we actually go to try to print this, we're going to first check to see if there's a sign, right? So if there's a sign and number sign is less than 0, then we're going to place at the buffer position ++ the negative sign. And then we're going to just iterate through it in reverse. And we're going to print out each of the different values. So just to make sure that you're really understanding exactly what's happening here. So when this function completes, it returns back to us the new number as well as the remainder. So the remainder is used to actually index inside of this array. And generally, this number is going to be divided each time by, for instance, 10 if we're working with decimal values. So eventually, it's going to be less than 0 because we will divide by 10 and it will end up as a smaller value, which is going to bump us out of this array. But before we do that, it's going to continue to get smaller and smaller. So for instance, if I had like 450, after the first division, it'd be 45. After the next one, it would be 4. Do you see how we can get the rightmost value each time out of that? And then by the last division, we would end up with something like 0 or something less than 0, which will boot us out of that loop. So this gives us the general way that we're going to print out our numbers. So at this point, the only thing really left to do is to implement this x86 div 64 32, which we're going to do inside of our assembly code. So our division code will be implemented inside of our print.asm file. In order to do that, we'll also have to add the function stub inside of the header for this print. So I'll just go ahead and set up my word wrap here so it's easier to read. And we'll go ahead and set up those two components here now. So the actual stub for this function we will do cdecl like this. And the name of the function was going to be x86 underscore div 64 underscore 32. It's going to take in a uint 64 underscore t as the dividend. And then we're also going to take in a divisor, which is going to be a uint 32 underscore t. So that's our divisor. We are additionally going to give back a result stored in a pointer. That's the quotient that is out from this, as well as the remainder that is provided. So those were the two pieces that were being used as pointers inside of our division algorithm. So if you remember, when we take a look at this stdio, these two values are passed in as pointers that we use them later. This is like a very rudimentary way of returning data back from assembly. We can simply place it inside of these address references and then use it inside of our code. So that's generally what we're doing here is we're using these essentially as return values. So to return two different values, we just put in two different addresses and send them back. Now inside of our assembly code, what we do is we do something similar to this write character teletype, we create a global function, and it's going to have that same name, x64 underscore 32. And we set up this label here, and we go ahead and set up our functions. So as with our other functions, we push on the BP in order to preserve that, and we move the stack pointer to the BP as well. We're going to overwrite the BX register, so I'm going to push it in order to preserve it. Now, when we're working inside of here, what we're going to do is we're going to do our division, and we sort of do it piece by piece. So what we do is we move in to EAX BP plus 8, which would be the first argument. Now, the thing about this argument is that it's actually a 64-bit value, right? It's a uint 64. So when we move this into EAX, EAX is a 32-bit register. So what actually happens is this is going to move in really the upper 32 bits. So we're going to do the division in two different pieces. So we do the upper 32 bits, and then we can do the lower bits of it as well. So that's what that's really moving in. Now, when we move to ECX, which is going to be our divisor, we do BP plus 12. So this is our divisor. Now, again, when we take a look at the way that we're setting this function up, when we're taking a look at that divisor, we know that the divisor in this case is actually a uint 32. So since this one is 32 bits, this actually moves the whole divisor in. So that's the difference between these two. Since this is 64 bits, this is just the upper 32 bits. Whereas since this is 32 bits, the whole thing goes into ECX. Now we're going to XOR EDX with itself in order to zero out that register. Remember, that's where the remainder of the division is going to be placed. We're then going to do a divide with ECX. So this will divide EAX and ECX and store the result in EAX. And it will store the remainder in EDX. So that's the way that that is going to work. Now to do the remainder of the division, we're going to move into BX, BP plus 16. This would be the location of the upper 32 bits. And then we're going to move into BX plus 4. We're going to move EAX into it. So we're essentially just storing the remaining result into this BX register, which is going to allow us to complete our division. Now from here, what we could do is we can move into EAX BP plus 4. Sorry, this is the upper 32 bits of the quotient that we're setting up here. This right here would be the lower 32 bits of the dividend, since it's at BP plus 4. So when you think about this, right, at 8, it's just past the first argument, whereas 4 is the first half of that argument. So that's why that's the lower 32 bits. This is the upper 32 bits. So we move in those bits, and then we do our division once again with ECX. And now we have the full result of our division. So from here, we can move into BX EAX like this. We can then move BX. We can give it BP plus 18. And then we're going to move EDX into that particular location. So what we're really doing here is we're storing these results inside of the registers that are the addresses or pointers that we placed in, right? So at BP plus 18, this is the one register that we have, and then the other one was at BP plus 16, right? So we set those both up to get our return values in place. And at this point, we're done. We can pop BX since we pushed it on to preserve it. And I can move BP back into the SP, and then I can pop the BP back off and return. And that's the end of our division. So this is really just a long division algorithm. So this is another way that we can divide numbers. I think I've shown some basic ideas of division throughout this series as well as my other x86 series, but this is another algorithm that's important to know about. So it's essentially just a way of being able to do long division. And this is very helpful for our scenario because we want to be able to control the sizes of our registers so that they're able to play nice with the code that we have set up currently. With this, we should have everything in place to be able to use our printf function. So it makes sense for us to test it out and see what is happening. Now, we may have some errors as we're going through this, and that's okay. It's normal to have some errors in such a long implementation, so we'll address those as we go. So I'm going to try some different formats. I'm going to do 2% signs, a %C, and a %S, just as some basic ones to try out. So %%, this is like an escape character, so it should just print this single % sign. %C is the first format. I'll have it print out the character F, and the string, I'll have it print out, I don't know, hello, as an example. Let's try to print that and see what happens. So if I come over here, I'm going to go ahead and build my my operating system here with my make. And you'll see here that we actually do get a few errors here. So that's okay. Let's just go through and resolve these. So I have one in standard.io.h. It says that there is a parameter issue. So let's go over there and just take a look and see. So in standard.io.h, which is right here, we have an issue with one of our functions. It says here at 7. It's having trouble with putting this together. Oh, this should be puts_f. That's the problem there. So remember, this is the var puts, so it takes in the var pointer, and this was the name of the function. I just had that incorrect. So that solves that error. So we'll go through another make here, and let's take a look at some of the other errors that are coming up. So we have another error at the standard.io.c line 16. Let's resolve this one here. So on line 16 of my standard IO, we're going to come up here. We're just going to take a look here. So we have, oh, again, I forgot to keep this name consistent. So that's puts_f. That should help to resolve a fair number of these issues. Okay, there we go. Let's see what other errors we have. A case must appear in a switch statement. So this is at line 32. Let's come down here and see. So at line 32, we have a case right here. Oh, I forgot to put the switch statement in. Okay, well, that's a simple thing to solve here. The switch that we're doing here is going to be based on format. So what we have inside of here is we have well format. Oh, sorry, we're doing a switch based on state, rather. So the switch here is going to be based on state. Here's the opening brace, and then the closing brace is going to come all the way at the end of all of our different states. Right down here, I believe. So that should be the location of that. I'll just make sure that that actually is the case here. So yeah, it looks like, so this is the closing brace bracket for this piece up here. So that should be all good. Now, one other thing that I realized is that I actually didn't increment format down here. So I should increment that so that it increments on each iteration of my loop. So we'll make sure to do that as well. Let's try to make again. Let's see if there's anything else that seems to be a problem. We can see here that there's an error of an expected semicolon on line 44. Let's take a look at that one here. So on line 44, I have my else if here. When I'm taking a look at this, maybe this should just be like an else if like this. I think that actually might be the problem. I've mixed up my syntax with other languages. That's okay. There we go. So line 181, the symbol post has not been declared. So let's just come down here to 181. Oh, yeah, just a misspelling. This should be POS rather than post. So it's position. And now we have everything up and running. So just little typos here and there, that's okay. It looks like we've got everything resolved now. So let's try to run this and just see if it actually runs. And we can see that it does actually look to be running. Do you see that we get %, and then F, and then hello? So you see that it printed everything that we were expecting it to print. That's great so far. I'm gonna do a few more prints because, well, we wanna really make sure that everything is dialed in and looking good. We'll try some numeric prints as well. Let me put a new line character here so it's easier to see the outputs. We'll do a few more printfs here. So let's do a printf with some numbers, okay? So we'll do a %d. Let's do a few other ones. We'll do a %i, we'll do a %x, a %p, and maybe a %ld as well. So 1, 2, 3, 4 maybe for this. We could do like a -1. For hex, we could do like 0x1a. For a pointer, that's also a hex. So maybe 0x3a, and I put in an LD as well, so that would be like a long integer value. So maybe negative, a whole bunch of zeros with an L at the end to indicate that it's a long value, and that should probably be good. Let's give those a try and just see if these are also working. So we'll make this. I forgot a semicolon at the end of this, so let's do that. Now let's make this, and we'll run. And you'll see here that everything looks to be printing as expected. So this is really great. It looks like our printf is up and running. So with that, you now see how to implement printf using a mix of C and assembly. So this is a really cool exercise of just being able to blend together C and assembly to be able to create functional things that we have available in the C library, but it's interesting to see how these things can be implemented from scratch. So this gives us our printf function. So thanks so much for watching, and I'll see you in the next video.